All right, so we know some things. We know that if a gas obeys the kinetic theory of gases, so if a gas has pretty much itself, if the volume of the gas molecules have zero volume, if the gases are in constant motion and variable direction, and if in particular they undergo elastic collisions, we've got a gas that we can ignore the volume of the molecules of, and they undergo elastic collisions, meaning in particular that they do not stick together, then we say that the gas is ideal. Now, if the gas is ideal, we can do a great deal of math with it. So that's our job, math with gas, ideal gases. All right, so we've got a gas here, and we're going to hold some things constant. We're going to hold the number of moles constant. And by the way, when we talk about gases, we're going to describe a mole as N, and we are also going to hold the volume constant. We're going to describe the volume as a V, and we're going to hold these guys constant as we do an experiment. So with our moles constant, container sealed, volume constant, it's not going to expand or contract. We're going to take our gas and we're going to heat it up. So as we take and we add heat, we know the kinetic energy of the gas is going to increase. As the kinetic energy of the gas increases, the gas is going to take and hit the sides of the container harder. And when it does that, our pressure is going to go up. So here, as the temperature of a gas goes up, the pressure of the gas is also going to go up. If we took a number of measurements and we graph this, we would find here a nice formula where as the temperature goes up, the pressure is going to correspondingly go up. Now, by the way, you can do this and you can actually figure out the temperature at which it has no pressure, and that temperature is absolute zero. With a note on gases is that when we do gases in any question that involves gases, our temperature must be in Kelvin. If we use any other temperature unit, it's got negative values and things start to make absolutely no sense. But we can get an equation out of this. If our pressure is directly proportional to temperature, we can say that P1 over T1 for the gas is equal to P2 over T2 for the same gas, with everything else held constant. So, law number one, P1 over T1 equals P2 over T2. All right, we can do the same thing with volume. If we take and allow the volume of a gas to change with temperature, in this case, this would be like you have a balloon and you take your balloon and you add heat, pretend that's a Bunsen burner, to your balloon. If you add heat to the balloon, the volume of your balloon is going to start going up. And as the volume of this balloon goes up, so as temperature goes up, the volume of the balloon is also going to go up. It's going to do that trying to hold the pressure in there constant, and we can get the same kind of equation. If we have the temperature and the volume, as one goes up, the other goes up, we're going to have V1 over T1 is equal to V2 over T2. And again, like any other equation in gas laws, temperature has to be in kelvins. All right, what about pressure and volume? Well, if we take a gas at a certain pressure and volume, and we're not going to allow the temperature to change, and we're not going to allow the number of moles to go down so the gas is nicely sealed, and we take and we compress it. So our volume goes down. Well, we're still going to have the same number of moles of gas in that container because none has escaped. So therefore, we've got more gases colliding with the side. So as the volume goes down, pressure is going to go up. Now this is an inverse relationship rather than direct, and this tells us that our volume is inversely proportional to the pressure, which tells us that V1 times P1 is equal to V2 times P2. As one goes up, the other one goes down. This, by the way, is Boyle's law. They all have names. There you go. They have names. All right, so we breathe by a volume and pressure change in our lungs. If the volume of our lungs goes up and the space increases, the pressure inside is going to become lower. Pressure in is less than the pressure out. And if the pressure in is less than the pressure out, then air goes in. If the volume in our lungs decreases, the pressure in is greater than the pressure out, and we breathe out. Remembering that air pushes, and it's going to be pressure pushes, and we're always going to push from the higher pressure to the lower pressure. Scuba diving is very cool. At some point, look up scuba diving and air pressures and regulators and realize how incredibly heavy air is on all the things that we have to do in order to survive underwater. Not just bring in the air, we got to bring the air here compressed so that we can breathe. All right, this gives us a bunch of gas laws. The first is Boyle's law, and the Boyle's law tells us that as the volume goes down, the pressure goes up, inverse proportionality, and our equation is V1P1 equals V2P2. Now, by the way, we write these in all sorts of different ways. You can also write this as P1V1 P2V2. The order is not sacred. Charles's law is a relationship between volume and temperature. We know as the temperature goes up, volume is going to go up, giving us V1 over T1 equals V2 over T2. Now, Gay-Lussac's or Aumann's law is a similar thing except for pressure and temperature. And if we hold our volume constant, as the temperature goes up, the pressure goes up, and our law is P1 over T1 is equal to P2 over T2. By the way, these are all on your equation sheet. And we also have Avogadro's law. Avogadro's law says if you've got something like a balloon and you blow into it, as the number of moles, N is moles of gas, goes up, then the volume is going to go up. So our equation is V1 over N1 is equal to V2 over N2. So let's use them. So if we have some argon in a light bulb, and this light bulb contains 1.20 atmospheres. So the first thing we're going to do is write down what we have. We've got a pressure, so we're going to call this P. Now we've got it varying, so we're going to call this P1. So if P1 is equal to 1.20 atmospheres at T1, which is 18 degrees Celsius. Now we know anytime we do gas laws, we have to put our temperature in kelvins. So if we do the math on this one, we're going to realize that our T2 here is equal to 291 kelvins. Remember, we add 273. We want to know what the final pressure, well, that's P2, is when our temperature is heated up and our gas bulb is hot, and our temperature is at 85 degrees Celsius. Well, if we add 273, we are going to get 358 kelvins. And then we find the right law. We want the law that relates P and T, which tells us that P1 over T1 is equal to P2 over T2. So 1.20 atmospheres divided by 291 Kelvin is equal to P2, which we're going to solve for, over 358 Kelvin. Please cross multiply this side over here, solving for P2. Since the temperature went up, our pressure is going to go up, and our final pressure here is 1.45 atmospheres. All right, so we have a sample of a gas. In this case, it's chlorine. It has a volume of 946 mils at a certain pressure, so we're going to call this V1. Our pressure here is 726 millimeters of mercury. Let's call that P1. We want to know what the final what the final pressure is if the volume is reduced to 154 mils. We want the final pressure. Now, we want it in atmospheres, so we better fix the number above so our units are the same, and it doesn't matter what units of volume or pressure you have as long as they are self-consistent. So because we start out in mercury and we want atmospheres, I'm going to fix this. That's 1 atm for every 760 millimeters of mercury, and that is going to give us a P1 equal to 0.955 atm. So our equation is V1 P1 is equal to V2 P2, so 946 mils multiplied by 0.955 atm is equal to 154 mils multiplied by P2, We divide through by 154, we are going to get a P2 of 5.87 atmospheres. Because the volume went down, the pressure went up, and this value makes good sense. All right, so we have a sample of a gas, and unless they tell us it's a real gas, we're going to assume it's ideal, so we don't even care what it is. And we have a volume and we have a temperature. So if we have a volume, let's say our volume here starting with is 3.20 liters at a temperature of 125 degrees Celsius, we know we have to put that in Kelvin. And when we put this in Kelvin, this is 398 Kelvin. We want to know if the final volume of the gas is 1.54 liters, what is the temperature of that gas? Well, the volume is going to go down, the temperature is going to go down. So we have V1, T1, and we are solving for T2. So our equation, V1 over T1 equals V2 over T2. If we plug this in, 3.20 liters over 398 Kelvin, our initial set of conditions, is equal to 1.54 liters divided by T2. Now we're going to have to cross multiply to solve this, and when we do that, we will get that T2 is equal to 192 Kelvin. Now this is good and cold, which also makes sense because the volume has gone way down. So the last thing that we do with these relationships is we combine them. We know that P1, V1, P2, V2, and we know that P1 over V over T1, equals P2 over T2, and we know that V1 over T1 is equal to V2 over T2, and volume over moles is equal to volume over moles. If we take and combine all of those, we can see that our pressure and volume are going to stay in the numerator, and our temperature and our moles are going to go in the denominator, and we're going to get a combined gas law. And our combined gas law is P1 over V1 is equal to N1 over T1. And we can use this when all four things are changing or any three are changing. This is just the combination of the whole lot. In fact, you could take and remove the entire denominator and get Boyle's law. So this contains all of the laws that we're going to work with. Let's do a problem. So we have a balloon where the volume is 1,500 liters at a pressure of 0.925 atmospheres and a temperature of 23 degrees Celsius. So let's call this V1, and we're going to call this P1. We know this has to be in Kelvin, so we're going to add 273, and we're going to get a T1 of 296 Kelvin. All right, so we've got some conditions. Now we're going to take and allow the balloon to rise into the atmosphere, and we totally don't care about that information. We just need the pressure, temperature, and volume. We want to know what the volume is if the pressure is equal to 2.25 atm, and the temperature is minus 50, and by the way, it is cold up there, degrees Celsius. Well, this temperature is going to work out to 233 kelvins. And now what we have is a bunch of things. We have P, V, and T. Now our moles are not changing, so we can just remove it from our equation, and we're going to have P1, V1 over T1 is equal to P2, V2 over T2, remembering to keep the two sets of conditions separate. So 1,500 liters multiplied by 0.925 atmospheres divided by 296 kelvins is equal to the volume, which is what we're solving for, times 0.25 atmospheres, so our volume has gone down a lot. Now it's cold, but not that much colder if we compare those two values. Mostly our pressure is going to go way down, so the volume is going to go way up. If we cross multiply and solve, we will get that V2 for this gas to 2 sig figs is 4,200 liters.